Our sun will one day swell so much it could engulf Mercury, Venus, maybe even Earth. But a star just a few times more massive ends its life in a supernova, blasting its guts across the galaxy. Some dead stars spin hundreds of times per second, flashing light like cosmic lighthouses. Others pack magnetic fields so strong they could fry electronics from thousands of light years away. From the smallest meteoroid to the mightiest supermassive black hole, today we'll map out who's who in the universe.
Starting from the smallest one, meteoroids are fragments of rock, metal, or both, measuring anything under a meter across, all the way down to grains of dust. When a meteoroid enters Earth's atmosphere and burns up, it creates the streak of light we call a shooting star. That is also what a meteor is, a meteoroid that entered Earth's atmosphere. And if part of it survives the fall and lands on Earth, it's now a meteorite, like the many that are visible in Antarctica.
Asteroids, though, are already in another league. Like meteoroids, asteroids are made primarily of rock or metal. They start at 1 meter across by convention, and their upper size limit is defined more by shape than by size. If they are large enough to become rounded, which happens when the rocky object is a few hundred kilometers across, these rocks approach the planet category. If not round, then it is still an asteroid. Another important part of the asteroid definition has to do with its orbit. Only objects that orbit the sun are called asteroids. If they don't, they are called interstellar objects like Oumuamua. Comets are not asteroids because comets are made of ice. They are icy bodies with dust and gas. Far from the sun, they're invisible, but when they swing close, the ice vaporizes, creating spectacular tails millions of kilometers long. The now famous 3I/Atlas is believed to fit this category. From the rocks and ice that crash into us to the giants we orbit, let's scale up. A dwarf planet is a body large enough for gravity to make it nearly spherical, but not massive enough to clear its orbit. This means that while a dwarf planet does orbit around a star, the path it goes through is not cleared of other rocks. Dwarf planets start at about 400 kilometers across, though exact size varies with composition. Pluto was demoted from the category of planets precisely because it shared its orbit with tons of other rocks. For a celestial body to be called a planet, it needs to fit 3 requirements. It must orbit a star, be large enough to be round, and have cleared its orbit of other debris. Curiously enough, composition doesn't matter. They can be rocky solid planets, like Earth, or gaseous, like Jupiter. Gas planets being usually much larger than rocky ones. A moon has a much looser definition than a planet. Its defining characteristic is that it does orbit something, and that something is not a star. Moons can orbit planets, dwarf planets, Pluto itself has one, or even asteroids. They can be large, like Ganymede, that is bigger than Mercury, or small and potato-shaped, like Phobos. They can also be plentiful. Jupiter has 95 confirmed moons, and Saturn 146. But when moons get really small, gravity, tidal forces, and collisions make individual orbits unstable. Instead of a single object, we get countless tiny particles sharing roughly the same orbital path. That's what forms rings, like those around Saturn. But every planet orbits something greater, and that's what makes the skies bright: the stars. Stars are giant balls of hot gas, but the essential characteristic of a star, and main difference from a planet, is that fusion happens at the star's core. That fusion is what gives stars their glow. In order for fusion to happen, an object has to be really massive, many times more massive than the biggest gas giant planets. The smallest star-like objects, the brown dwarfs, are called failed stars because they are still too small to ignite hydrogen fusion, even though they are still at least 13 times more massive than Jupiter, the biggest gas giant planet in the solar system. Brown dwarfs fuse deuterium and maybe lithium and glow only faintly in infrared. The next category of stars are the red dwarfs, which start at about 80 times the Jupiter mass, or from 0.08 solar masses. They are relatively cool, burning hot of course, but cold when compared to other stars. Red dwarfs are also dim and long-lived. They can burn for trillions of years and make up about 70% of all stars in the galaxy. At around 0.5 solar masses come the orange dwarfs, also long-lived. These are slightly bigger and hotter than red dwarfs and have longer lifespans than the sun, making them good candidates for creating stable habitable zones. Next come the yellow dwarf stars, the category where our sun fits. They range from 0.8 to 1.2 solar masses and can burn for about 10 billion years, a bit less than the whole age of the universe so far. White stars are even larger, hotter, and brighter than the sun, but they burn through fuel faster, lasting just a few billion years. Then come blue-white stars, bigger, hotter, and more luminous than white stars, with lifetimes limited to hundreds of millions of years. Sirius, the brightest star in our sky, is in this category. Next come the blue giants, which are massive, weighing from 2.5 to 16 solar masses, and extremely luminous, burning out in just tens of millions of years. Finally, the O-type stars are the rarest and most massive main sequence stars. They are hundreds of thousands of times brighter than the sun, but last just for a few million years before going supernova. So, stars face a trade-off. The more massive and brighter they are, the less they last. And that impacts our chances of finding life elsewhere, as if a star provides energy for just a brief period of time, it is probably not going to be enough for life to develop and evolve before being engulfed by the star itself. And engulf they do. At the end of their fusion period, when stars run out of hydrogen, they enlarge. Stars like the sun swell enormously, burning heavier elements. One day, our sun will expand enough to swallow Mercury, Venus, and maybe Earth. Stars from the higher end of red dwarfs to blue giants share this fate, and their enlarged state is called a red giant. A star can last from millions to a few billions of years in the red giant phase. A red giant is not to be mixed with a supernova, which is the end stage of the blue giants above 8 solar masses and of the O-type stars. The supernova actual explosion event is extremely brief, just seconds to minutes for the core collapse, but the visible light show lasts weeks to months before fading. A supernova is a spectacularly violent instant that reshapes galaxies. After the red giant phase, the remains of the original star become a white dwarf, not to be mixed with a white star. A white dwarf is not a star as there is no fusion going on. White dwarfs are dense, Earth-sized but as heavy as the sun, fading heat across the universe. But the remains of a supernova, these are staggering. They are called neutron stars, even though they are not stars at all, but just the remnants of what was once a massive star. They are about 100 million times denser than the already packed white dwarfs. If a white dwarf could pack the weight of the sun in the size of Earth, a neutron star could fit in the size of a city. Neutron stars may glow from residual heat and emit radiation via magnetic activity, but this is not fusion. All neutron stars rotate around their axes, and some have a misalignment between their magnetic axis and their spin axis. When this happens and the rotation is fast enough, the neutron star produces a beam of radiation, like a cosmic lighthouse. If this beam sweeps past Earth, it is visible to us. In this case, this particular type of neutron star is called a pulsar. Pulsars are some of the most precise natural clocks in the universe. The fastest pulsars, called millisecond pulsars, can spin hundreds of times per second, and the fastest one we know of spins 716 times per second. Their pulses arrive with better precision than atomic clocks on Earth over long periods. Pulsars rotate with astonishing regularity, so precisely that astronomers use pulsars to test general relativity, detect gravitational waves, and even measure the motion of our galaxy. A magnetar is a special kind of neutron star with an extraordinarily strong magnetic field, 1,000 times stronger than a typical pulsar. Only neutron stars born from very massive stars, between 10 and 25 solar masses, with rapidly spinning cores, can generate these fields. The spinning core acts like a dynamo during collapse, amplifying the magnetic field to levels so extreme that it triggers violent bursts of X-rays and gamma rays. No, really, a single flare from a magnetar can release in 0.2 seconds as much energy as the sun emits in 100,000 years. Magnetars are tiny city-sized objects, yet they can destroy satellites and fry electronics from thousands of light years away with a sudden flare. And if you were 1 light year away from one, the radiation of a magnetar would be enough to kill you, destroying your cells.
Now, before we get dizzy, let's go from spinning lighthouses to objects that bend reality itself, because some objects don't just shine, they devour. Every time a star runs out of nuclear fuel, it collapses under its own gravity, and a core is formed. If the star was very massive, about 18 or more solar masses, there is a chance that the remnant core's mass reaches as much as 2 to 3 solar masses. And if that happens, the core becomes not a neutron star, but a black hole. Astronomers estimate that there are tens of millions such black holes scattered across our galaxy. The largest among these phenomenal objects are called supermassive black holes. They can either come from direct collapse of massive gas clouds in the early universe, or from mergers of smaller black holes or stars over time.
Supermassive black holes sit at the center of galaxies, like Sagittarius A star, that is in the center of our own galaxy, the Milky Way.
From meteoroids to supermassive black holes, understanding who is who reveals the astonishing order behind the chaos and reminds us that our place in the cosmos is as fleeting as it is extraordinary. Thank you for watching, keep marveling at the stars, and if you enjoyed this journey through the cosmos, please give us a like.